Okay, folks, welcome to the cool session on hybrid planning. Miguel will start.
Okay. Hello, everyone. I'm Johannes Massa, and this is a joint work with Miguel and I'm going to talk about the semantic notion of interference for PNT. Okay, we will start with an introduction. In fact, the parallelism has been one of the main factors that has brought planning as such to the state of the art. It's the fact of executing various actions at the same time step. Classically, interference between actions has been checked syntactically, but yes. Hello? One, two? Okay. And when you have to reason about other things that are not propositional variables, it gets much more complex because you have to add information about the theory into the syntactic chain. And it becomes non-trivial. Okay, the first attempt we had at this was an article at the last year at Coppola. And our aim in this work is to obtain more parallel plans by reducing the amount of interferences between actions. But first of all, let's talk. What is PMT? PMT it's the fact about planning beyond propositional to be able to reason about other things like time and numbers. I'm not going to give a formal definition here, but what you have to have in mind is that our state space we expand it with a modulo T. Okay, so we have propositional variables and variables that belong to the T, and our preconditions are expanded to be first-order sentences over this state space. Some of you may be familiar with planning aside, but some of you know. So roughly, to solve a planning aside, we consider a sequence of formulas phi sub 0, phi sub 1, phi sub 2, etc. And each one of those phis encodes the feasibility of a plan of exactly that number of time steps. Depending on the semantics we are considering, a linear plan for all or exist step semantics, we can have one or many actions in a time step. And of course, we expand the formula linearly for each time step we consider. Okay. So in our case, we can see that if we can cram up more actions in less time steps, we have to check less formulas. But what is inside each one of those phis? Okay, it basically boils down to three constraints. The first constraint says that if an action is executed, its preconditions are true at the start of the time step. The second one says that if an action is executed, its effects hold at the start of the next time step. And finally, the explanatory frame actions that, as you all know, say that if the value of a variable has changed, it means that some action that could change the variable has been executed. And the existing step semantics, that is the one we used on the paper, well, here is the definition, but it's very simple. It basically says that at each step we consider not only one but a set of actions, and there has to exist one order that can bring you from the previous state to the next one. Okay. In planning a set, it's normally required that you can linearize a parallel plan. So, to guarantee that at least one order exists, one of the simplest methods is to enforce a total order between the actions, and at mutex, if the first action affects the second and comes before it. Most notions of interference in the literature are slight variants, and all of them do a semantic check. They express that in different ways, but most of them basically says that if the first action can modify the effects of the second, prevent its execution, or their effects are not coherent, we say that the first action can affect the second. To see what we are talking about, more or less, here are it's a little snip of the problems we try to solve. And we can say that if on the smallest ones, we are talking about thousands of applications for each time step, and on the biggest one, we are talking about millions. So it's a pretty big number. Okay, now that we have laid the ground of the introduction, let's talk about the semantic notion. The basic idea is to encode in a formula the possible interference between pairs of actions. We just have to check the satisfiability of this formula, and if it's sat, we add the interference to our graph. Note that the interference relationship that we get with this method will be always a subset of the interference relationship we can find syntactically. For example, the effect of increasing the fuel of the truck by 10 can never impede the execution of an action with the precondition that says that the fuel of this truck has to be greater than 0. For us, it's obvious, but for a syntactic check, it's not, because the syntactic check has to know the meaning of the greater than and the increase. We will start by defining what is two commuting assignments. If we have assignment 1 and 2, two assignments are commuting if the application of the assignment 2 on the first assignment is the same as applying the first assignment to the second. If those two formulas have the same number, well, the same models, that means that they are commuting. For example, if we are talking about the reals, then if we increase the x by 1 and decrease the x by 2, we know that it's the same if we do it in one order or the other. Two simply commuting actions are if for all the variables of the state space, or every pair of assignments of those actions are commuting. And we finally define what is happening. Okay, happening. It can be seen as a meta action that is It's the conjunction of all the actions that appear in a time step. The preconditions of these actions is just a conjunction of all the preconditions, and the effects is the union of the composition of the functions for each variable. Okay, now we can define having this, what is an unaffecting action. Given two actions, the first affects the second. If the first can impede the execution of the second, this can be expressed as the preconditions of the two actions are true, and the effects of the first action negate the precondition of the second action. And the second thing we require is that executing first A and then B have different effects than the happening of A and B. So, in some sense, we're saying that the order of the execution matters. So we can express this with saying A and B are not simply commuting, or the two actions can execute, and the happening of the actions A and B is different from applying sequentially all the effects of B and then all the effects on A on the variables. To see an example how this works, here are two actions of boarding one person on a plane, and that plane flying from city 1 to city 2. The important parts of the actions is that on board we increase the on board by 1, and on fly we require that there is somebody on the plane to fly it. This is how the formula would be expressed in SMT. We simply declare the variables, we assert the preconditions, and here we assert the negation. Okay. The relevant parts of this formula are the precondition. It's that on board plane 1 is greater than 0. The effect is just on board plus 1. So if we substitute the effect on the precondition, we get this. Okay. So if the applied effects on the precondition of the first action can make the formula true, this means that the first action would affect the second. Okay, now that we have the semantic notion, we can see our encoding. If we encode naively two effects like this, increase the fuel of the truck by 10 and by 5, for us it's obvious that those two effects can be executed at the same time step. But the classical encoding would say that the fuel of the truck on the time step 1 has to be the same as 0 plus 10 and the same as 0 plus 5. Obviously, this formula is unsatisfiable, so we need more intelligent encoding. The idea of this encoding is that we create a chain of assignments for each action that can modify this variable. Okay, I'm not going to introduce formally the encoding here because I have no time. But the idea is that we create these extra variables that keep that it's like keeping a stack on the modifications of the effects of each action. Okay, now that we have presented the notion and the encoding, here we can see that on the same instances we presented, the reduction on the number of time steps is interesting, and the number of affectations are reduced normally between 1 order of magnitude or even 2. On the number of time steps, those are the commonly solved instances for each approximation. And we can see that the number of total time steps it's very low. Okay, as conclusions, we can say that we succeed in improving the well-known notions of interference. We started to work with only numbers, but we realized that this notion can really be generalized to any theory. And this semantic notion, it's elegant, it's compact, and what's most important, I think, is that it can be easily implemented for any solver that it's important to him the number of interferences. Thank you very much, and if you have some questions.
A few minutes for questions.
Hello, thanks, good talk. I was just wondering what happens if you have multivariate conditions. So say I have two batteries and I need the sum of the battery power to be greater than or equal to 10 or something, or a battery tank and a different type of fuel tank. It seems that would introduce some kind of disjunctive constraints. So can you handle that?
Yes. Yes, the notion of interference between, I think what's important here in the definition is that we handle the simple commutativity assures you that it's not important. We check one action and the other for every pair of actions, and here we guarantee that it's the order of the actions. It's not important. So it's what's useful this for is for when you modify various variables at the same time step, you can guarantee that the combination of all the executions it's not important for the order. So that's it.
Any more questions?
So I noticed that even though the number of steps decreased, the solution time increased with the
Yes.
new encoding, right?
Because as we add extra variables at each time step, the number of variables on the problems it's increased. So the problem becomes bigger, but we are more scalable. So in the problems that are very small, it is noticeable, but there are some problems that normally as you have. I think that as the formula grows linearly in size, okay, even though you have less variables, there you reach one point that the solver cannot handle that number of that size. So it's so the extra parallelism it's beneficial to you in this sense.
Thanks.
So there is a very similar mechanism in Shin and Davis' work. Have you looked at that? So I mean, they basically compile PDDL plus problems in something that now we will call SMT, right? Because it was SAT plus and external swap at that time, and they have a very similar concept to collect the contribution of many actions, and so they have the same concept that you have to accumulate the values of a given variable by many actions. So they have this. You may have a look at that.
Oh yes,
Yeah.
thank you. If you can give me the reference. Thanks.
Final questions?
So, do I understand correctly that you handle interference in a different way, and also you handle now numeric domains via the theory? Is the power coming from the extra interference or from handling the numeric domains in a smarter way?
Correct.
So in your final slide, when you do the comparison, there,
Yeah.
is the extra power that you see here, does it come from a better handling of the numeric domains, or does it come from your extra interference handling?
Yes, it comes from the extra interference handling.
So the numeric domains here are not very large, and if you would not do the extra handling, but you would have a better handling of the numeric domains, you couldn't see this dramatic effect.
As we do an approach to planning as SMT, this really depends on the theory you are using on the background. Possibly, we used LIA, it's linear integral arithmetic, but some of the domains we used are very simple. So we have to explore if we could translate them to just a different logic. That it's a more cheapest theory. I think it's polynomial in complexity or something like that. I have to check, but yes, it is.
And have you considered other theories, like, for example, global constraints to handle the scattering part, if possible?
No, but that's a very interesting way, because I think the next step in using planning as SMT is to follow the same way as Rintanen did. That is, just stop treating the solver as a black box and start changing the heuristic you use, or the representation of the clausulas in memory. So a good idea would be to add global constraints to handle some specific structures that the planning problems have.
Okay, let's thank our speaker. Okay.
On this mouse is not working.
Yeah, I agree.
Yeah.
You put this on.
Can I start?
Yes, please.
Okay. So welcome to everybody. I'm Enrico Scala, and this is a joint work with Miguel Ramirez, Patrick Asrum, and Sylvie Thébault. As you may see from the title, this work is about numeric planning with disjunctive global constraints, and we use satisfiability modulo theory as computational framework. So when you have to plan for realistic world, you do need to have expressive models of the world. In these expressive models, you want to have you need to reason both on qualitative conditions and quantitative conditions, and the reasoning has to be done in an integrated way if you want to handle the problem. In quantitative conditions, in particular, you may have numbers, and numbers are necessary if you want to represent, for instance, resources, if you want to represent time, distances, and even geometric information. And the usage of numbers has not to be considered limited just to the case of the cost of the plan. The sequential decision making that is at the basis of this integrated reasoning is actually a building block for the development of any hybrid planning engine. So it's one of the motivations that drives us in this work. Last but not least, quoting recent work here at ICAPS, expressiveness, does not always go in contrast with efficiency, and we will see why. a classical example in which you do have to have this integrated reasoning between qualitative and quantitative condition is the one when you have to combine navigation problems and task planning. So let's take the rover, this rover example from the planning competition, but reformulated in a way to stress the numeric part of the problem. So you have this rover that has to reach the top position there in the map, and then on the way you have to collect information on those sites, okay, T1, T2, T3, and T4. Okay, so a sequential numeric planning and coding of this problem requires just 8 actions to describe the movement of the robot. We are considering the 8 compass directions, and those actions are completely numeric. They just describe that the rover is increasing the variable x or the variable y, or both of them if it is moving diagonally. And we have actions to actually capture the fact that we are collecting information in those sites. Okay. So, of course, the rover has to avoid the obstacles in the map, and one of the challenges, so, okay, a solution for this problem would be to go left for a given number of times, then to go up into the map, collect information, go south, left, up, and then finish the plan. What are the challenges here? The challenge here are that you have to deal with very complex constraints, which are determined by these obstacles and by the fact that you need to ensure that you are inside specific areas when you want to collect information. And of course, solutions can be very long, okay? Because I'm just saying that I have 8 actions, and every action just make little increase in this state space. Of course, the length of the solution depends on the step size, but you may want to have this step size reasonably small if you want to increase the chances to actually find the plan in this problem. Okay? And even worse, this is probably one of the worst examples that you would imagine if you want to tackle problems using SMT. So this was another challenge that we tried to address. So, of course, we are not interested in that specific problem that we use just as an illustration, but we are interested in sequential numeric planning with global constraint. In sequential numeric planning, you have variables that can be both propositional and numeric. You can have actions that can have numeric effects, and numeric effects are state-dependent operations. This is different from the classical case where the operations are state-independent, okay? If you don't have conditional effects. And the precondition of the action can include both propositional condition and numeric conditions, and you have goal and global constraints. Global constraints and goal can be expressed using quantified free formula over X, and our focus is on a deterministic setting in which we know the initial state, and the actions induce deterministic transition. Okay, so this is the framework, our target language. Another focus of this work is about the linear numeric constraint. A linear numeric constraint is basically a linear combination of numeric variables. Okay, it is an inequality between a linear combination of numeric variables and a constant, but with the possibility of expressing disjunction, the interesting thing is that we can represent very interesting problems. For instance, our obstacles are encoding as disjunction, and those disjunction actually represent non-convex regions. So we can handle this kind of problem. We use as computational framework satisfiability modulo theory. Satisfiability modulo theory is basically an extension of SAT, okay, where basically you can combine many theories, and in particular we are interested in combining propositional logic and real and integer arithmetic theory. As we inherited the classical schema of SAT-based planning, where basically our approach is an iterative deepening procedure over bounded planning problems, okay, and we stop as soon as a solution within a given horizon is found, okay. What are the issues here? The issues, as it has been hinted at before in the previous talk, are that the complexity of the problem grows, of course, with the size of the formula that you are dealing with. And this formula gets bigger depending on the horizon at which you are looking for a solution. So in the classical setting, previous work have tried to address this problem, proposing extended plan semantic, such as for each semantic, existential semantic, where basically the idea is to try to compress as many actions in a single time step. Okay, so the more you compress action in a time step, the more efficiency you gain. Okay, so the question that we asked here is, what about numeric planning? So what about numeric planning when you can exploit satisfiability modulo theory as a computational framework? One of the main ideas, starting from the observation that actually numeric action are not idempotent operations. If the repeated execution of the action leads to a potentially unbounded number of reachable states. Okay, if you repeat the same action over and over, the set of states is always different. Okay, and of course, I mean, this is a problem from a reachability viewpoint. Okay, but is it always a problem? And actually, no. But because if you, the idea of this paper is to try to find a way to represent, okay, those reachable states, okay, that are reachable by this repeated execution of this action in an implicit way. If you can do that, okay, basically what you can do is to compress all this repetition of the action inside a single time step. We call this technique rolling up, okay? And this is an example. This is one of the sub-problems that you can get in our motivating example. You have to reach position red starting from position green, okay? So what you really wanted, and you have an obstacle there in the middle, what you really want in this kind of problem is that you want to focus just on the relevant point. Okay, what is the relevant point here? Is the magenta point. You want to go from the green point to magenta to the magenta to the red point. You don't want to branch, okay, over all the possible intermediate states. So how can you capture this thing? So it turns out that under some conditions you can express numeric actions, and in particular the numeric effects of the actions in closed form. The conditions allowing this kind of situations are that the action shouldn't have self-interference effect, which means that basically the value of each variable that is affected by the action does not depend on some other variable that is affected by the action itself. Okay, and this is basically. Do I have a pointer here? Yeah, and this is basically this formula here, and that the numeric effects have to be linear. Numeric effects are linear as long as the expression here is a linear expression. Okay, so when an action respects that particular property, then we need to extend our axiomatization using these two elements here. Instead of considering actions, the action variables as propositional variables that tells us basically that action has to be executed at that time step, we say, okay, the action is an integer variable, okay, and the integer variable represents how many times I need to execute that action, okay. And this is for the action variables, and the effects are described in this closed form. This closed form is actually turns out to be a special case of closed form that you can get in the discrete event system literature. Okay, so basically here what I'm saying is that the value of the variable y, okay, can be modified by the action a, okay, and after m time the value of this variable here is this thing here. Okay, this thing here depends on the coefficient of the variable being affected. This is the and this is extracted directly from the model of the action. This is the coefficient of the variable being affected. This is the counter, okay, and this is the right-hand side of the effect. Okay, so Of course, you can do that, okay? But what's the problem then? The problem is that if you allow uncontrolled rolling up, then you can get invalid plans, okay? Because you can, on one end, you can violate your own precondition, okay? That happens whenever the action has interaction with the precondition of its precondition set, or you can violate the global constraint. Okay, so you have these two problems here. How do you, so this is an example of, this is the previous example in which, in this case, we also have an obstacle here. As you can see, if you do the rolling up, okay, easy, you can jump into this point here, the magenta point, but you will violate this constraint. So how can we deal with this problem? So we need to identify conditions, okay, for obtaining valid plans. So the idea that we pursued in the work is to use regression, okay, as a mechanism to capture what are these conditions. Basically, the regression is used to understand what are the necessary conditions for any condition in the problem that have to be satisfied if that action is applied. Okay. Regression can be defined in numeric planning. It is a syntactical operation, and the operation is basically a substitution which substitutes the value of it substitutes the variable with the way those variables are modified by the action. Okay, so for instance, for the action preconditions, we added this axiom here. Okay, basically, which this axiom says that if the action is repeated more than one time, okay, this thing here has to be satisfied. This thing here has to be satisfied means that this guy here, which is the regression of the precondition of the action, is this guy here is basically is a linear combination where every variable, okay, is modified with the closed form that we have seen so far. If this is true, okay, plus the classical axioms that you generate with your encoding, then you are sure that you are not violating the precondition. Okay, is this true? This is true. When does this? When is it true? This thing. This is true whenever the closed form that we have presented before is monotone, okay, in the number of times the action is repeated. So the intuition here is basically the fact that if this thing here is monotone, okay, you can reason just on the extreme points of your execution. You can reason on the starting point. You can reason on the end point, and everything that is in the middle will be satisfied. Okay, so this is basically the intuition. You can do that also for the global constraint, okay, when they are conjunction. The problem is that when they are disjunction, okay, so when you have disjunction, and we do have disjunction because we have these holes in our states, we can have these holes in this state space. When they are disjunction, then the situation is more complicated, and we implemented this mechanism, which is basically a reasoning by cases, okay? So the problem here is that when you have a disjunction, since you don't have this kind of monotonic property, then you have to understand what are the subparts of your disjunction that still can be considered monotonic, okay? So since we have linear constraint, okay, what we do is that basically that we take every disjunct of this disjunction, and then we intersect the disjunct of the global constraint with the condition regressed through the action. If this guy here is true, then I can do the rolling up. Of course, this represents just a sufficient condition that doesn't represent all the possible rolling up that I can do, and this is an example, okay, in which this can happen. We can capture a situation like that, okay, but we cannot capture a situation like that. So basically, we cannot capture a situation like that because the constraint that was satisfied in the beginning is not the same. It's not the same constraint that is satisfied after the rolling up of the action. Okay, so we can do this compression here. We cannot do this compression here. Okay, because it's a sufficient condition. So how much time do I have? 2 minutes, okay. So we run experiments on a variety of sequential numeric problem. We implemented this planner, so all these axioms are actually generated automatically. We use Z3, but also CBC4, but performances were very similar. So this is the Rover without task. This is no rolling up, the red line here, and this is rolling up. As you can see, there is so the speed up is of several order of magnitudes, and there are many instances that actually cannot be solved here. In the non-rolling up case, there is actually a positive thing because we already know the plan length, while the rolling up here is the old iterative deepening procedure, but that was the only way to actually measure this thing. Okay. So yeah, the instances here scale on the number of obstacles, but not on the size of the grid. Okay, because basically in this approach here, the size of grid doesn't affect the performance of the system, and that's because we are not actually encoding the grid explicitly, but the grid is implicit and is on the effects of the action. Okay, so situation gets a little bit worse when we have to deal with also with tasks, and we have instances here that are not solvable. And the reason for that is that we do need to have other plan steps to characterize the other actions. Okay, so something, maybe something, some kind of existential semantic has to be thought in this situation. Here we have other problems from the sequential numeric planning benchmark suite by Frances and Geffner, and we measured performance against FS0, which is the planner by Frances and Geffner, and the metric FF. Okay, and yeah, you can see here there is a big margin of instances which are solved by our system and are not solved by those two numeric planning. It's not always the case, because in this problem here we don't solve half of the instances that actually FS0 solves. And here you see the average time with respect to the other two systems. This last table show actually the more in-depth the benefit of the compression technique. Okay, so here you have the domains, here you have the plan length, the average plan length that has been found, and here the number of plan steps that you need to solve this problem. As you can see, counters grouping turns out to be super easy. Okay, with this encoding, because you can actually execute all these actions in, you can execute all these actions repeated in parallel. Okay, and of course it is not always the case, because when for instance in gardening you need more plan step, but of course there is still some compression here, and of course the time here increases when so the higher is the number of plan steps that you need, and higher is the time that you need to actually find the solution. How much time do I have? 0, okay. Okay, yeah, conclusion is basically that SMT is very powerful, but of course you have to inject some planning knowledge to actually make it scale up. You have to exploit numeric structure, and you have seen that actually you can. There are limitations, because SMT solvers are good when you have linear expression, but they kind of don't work when you have a situation more complex, when you have nonlinear expression, because the theories become undecidable. So as future work, we have to understand whether we have to jump into some new formalism or do something different. And that's all.
Okay, 1 or 2 questions. Could you jump forward?
So one of the key tricks, or maybe the key trick, is the rolling up, right? Can you comment on whether we could roll up also in like a forward state space search? You know, you're using SMT, and my question is, could you also roll up in other searches?
Definitely. The thing is that then you need to have some kind of SAT system to check the consistency, because you have the number of times is still a variable. Okay, then you have to decide how many times I need to repeat. Yes, in principle you can. Okay, but the challenge there is to understand first of all how to deal with the overhead of doing this satisfiability checking. Okay, to this existential checking there. Or maybe you can extract that information from the heuristic. That is another option. Yeah, definitely. I mean, the idea is actually this observation that you have non-idempotent operation, and you have to exploit that can be definitely used also in state space search. Yeah.
Okay, so while Michael sets up, we can take the question.
So the example you showed looks very similar to jump point search.
Yeah, the thing is that jump point search is for path planning, right? Yeah, this is, but yeah, definitely, because I mean, what you want to aim is actually to jump, okay, over different points of the grid in that example. So I mean, this can be seen as a generalization of that, right, for sequential numeric planning, and yeah, definitely.
Okay, let's switch over.
Okay.
Michael was last.
Nope. Oh, that's why.
Control L.
Oh, L. Sorted. Hello, am I loud enough? Yeah. Okay, I'm Michael Cashmore, and I'm also going to be presenting planning through SMT. In this case, PDDL plus planning. Our planner is called SMT Plan. This is some work we did here in KCL with Maria Fox, Derek Long, and Dan Magazzini. Okay, PDDL plus is an extension to PDL 2.1 temporal numeric domain problems, in which we also have events and processes. These model exogenous effects that the planner has no control over. An event is similar to an action, an instantaneous action, in that it happens at a single time point and its effects are applied. It's different in that when its precondition becomes true, an event must be applied immediately. Processes are analogous to durative actions in that they express continuous numeric change throughout an interval. When their precondition holds, the numeric change must be applied, and when the condition doesn't hold, then it can't. So our compilation is very similar to the previous two you've just heard about. Similar also to the original SAT plan compilation to a Boolean formula, or TMLP SAT into LCNF. One difference is that we are dealing with a non-linear polynomial change. I'll talk about some of the difficulties Enrico mentioned in a little bit. So we bound on the number of happenings. A happening is very similar to a planned step in that it's the description of the state at a single moment in time. Between happenings, there is only continuous numeric change. All of the discrete change has to happen within a happening. But the happenings, the length of this interval is arbitrary. It can be as long as you like. Okay. So I'm going to go into details on two features of our encoding which address some of these problems. First of all, event cascades, and then the zero crossing problem. So an event cascade is an issue that arises from instantaneous events. The events, as I said previously, when its preconditions become true, the event has to be applied immediately. And also, unlike an action, an event can make use of effects in the same time point at which they're applied. There's no epsilon separation. This means it's possible for one event to be triggered in a happening, and for its effects to trigger a second event, and so on. You end up with this causal chain of cause and effect, all happening in an instant time point. So whatever set of variables and constraints we use to describe a happening has to take this causal chain into account. The second is a problem that we get from having nonlinear change. So if we just had linear change, it's possible to check the constraints over numeric variables simply at the boundaries of an interval. So we could, for example, check at a happening here and here that this linearly changing function doesn't cross some threshold value, and that's fine. But when we move into nonlinear dynamics, then it's no longer sufficient, because we could have some function that violates the constraint between the interval, and we would never see it just checking at the boundaries. So we have to, in some way, include constraints that describe the numeric change over an interval to deal with this problem. So I'll talk a bit about the event cascades in this encoding section, and then the zero crossing problem in the algebra section. But first, I'll briefly describe the architecture of our planner. So we start by using a computer algebra system to perform some integration and differentiation on the numeric change as it's described in the domain file. So this is, done in a sort of lifted way. Here it says we use SymPy. We also use Pirano if we're in C++. The values derived from here are then used in the translation along with the rest of the PDDL description to create our encoding. And we put a bound on the number of happenings. So say 2 happenings with 1 interval of numeric change. The logic we're in is quantifier-free nonlinear real arithmetic. So we've got nonlinear dynamics in a deterministic situation. Then we pass the resulting SMT formula to a solver. We also use Z3, although I'll try the other one. If it produces a model, then this model describes a valid planned trajectory, and we can just extract the variables that represent which actions we're supposed to apply, and that's the plan. If the solver returns that there is no model, then we increase the bound on the number of happenings and translate again and again until we go home. Right, I'll now describe the encoding. These circles here are each set of Boolean and real variables that describe the happening. First of all, we have a single real variable for each happening that describes the time point at which it's occurring. And then we have sets of Boolean variables which describe which events are being triggered at this time point. So E0 here are a set of Boolean variables describing which events are being triggered at time t. E1 is then another set of Boolean variables describing which events are being triggered as a result of the effects of the events in E0. So you can see here we end up having this causal chain of events. This is the event cascade. We also have Boolean and real variables to describe the propositions and fluency in the state. And then at the end, we have a set of Boolean variables describing which processes will be active over the next interval. And at the top, a set of Boolean variables describing which actions can be applied in this happening. These are variables that the SMT solver will probably focus its search upon. Yeah. The next happening is constrained to appear at least epsilon after this one. So the next set of actions will check for its preconditions in the first set of propositions and fluents in the next happening, which is at least epsilon time after this one. B here is the second secret bound that we have, which is the bound on the length of the causal chain of events within a single time point. This can also be changed when running the planner. But in general, you don't have to set it very high. At least we haven't found any problems in which the length of the causal chain of events is extremely large. So then, to encode the whole plan, we simply chain together copies of this structure up to n copies, where n is the bound on the number of happenings. And we include constraints to describe the continuous numeric change between pairs of happenings. I should say, we also say that there's an initial state and a goal state. Quite important. Okay, now I'll go back to discussing why we use a computer algebra system at all, and how we use that to deal with the non-linear dynamics of the problem. So suppose we have this process running in a PDDL problem in which there's an effect to increase the velocity by the acceleration of the time. And that the rate of change of velocity with respect to time is the acceleration. It's very simple. We'll automatically perform some indefinite integration upon this expression to get a total value of the amount of change in the velocity over the whole interval. So this is some example Python code from SymPy, and it will give us the expression that we're looking for. I just omitted the constants of integration and such. So then in the SMT encoding, we can include that the total change in the velocity over the interval I is just the duration of the interval multiplied by the acceleration at the beginning of the interval, since acceleration in this problem is constant over the whole interval. And then we say that the velocity changes by this amount. And quite easy in this case. But suppose we now have a non-linear process here, where distance is changing with respect to time equal to v. When we compile this into the computer algebra system, we want at the end a formula for distance in terms of time. So we end up getting that the change in the distance over the interval will be a half acceleration times squared. And in exactly the same way, we can include these constraints into the SMT formula. And the computer algebra system is able to handle the substitution of other changing functions before integration. We also have this precondition that distance must remain greater than 0 over the whole interval. So, as before, we'll simply check that the distance remains above 0 at the beginning, at the end of the interval. But, as I said at the start, that's no longer sufficient, because distance is changing non-linearly here. If the velocity is initially negative and the acceleration is positive, it's possible for the distance to drop below 0. And if we're only checking at the boundaries of an interval, it's possible we could miss a violation of this constraint. So we need to do something else. This is why we also perform some indefinite differentiation in SymPy or in Piranha. We take derivatives of the function of change until the derivative becomes linear. And then we add a new constraint that the derivative at the beginning and at the end of the interval multiplied together is greater than or equal to 0. That should be a greater than or equal to. That is, the derivative does not cross 0 inside the interval. So as a result, between two happenings, not only is there only continuous numeric change and no discrete change, but between two happenings, there are no maxima or minima in the values of functions. I should say this is why we are restricted to polynomial nonlinear change. If we have a nonlinear function for which we can't find a linear derivative, then we won't be able to do this. Here are some results for a few of the PDDL plus benchmarks. mainly different variants of the generator domain, including the in which the fluid pouring is modeled using the Torricelli equation. In these problems, we outperform forward search quite a bit, since there's a lot of time involved with very few happenings. Okay. These are the times from the paper, and they don't include the time taken to perform the indefinite integration and differentiation. However, the times on the website do, and you'll see that they're basically the same, since the time taken to solve here is just dominated by the search, by Z3. Okay, the solver is now on the website, and you can download the source code if you want to play with it. It's for you. Okay, any questions?
Okay, can we answer your questions?
I'm just curious which solver you took, SMT solver. In your presentation of the results, you had dreach, and which is your SMT solver?
So we are SMT plan plus. This is the PDDL plus solver. So dreach is solving the PDDL benchmarks.
So you compile and then call the SMT solver or not?
So yes, the SMT solver we use is Z3. Yeah.
Questions?
Hi, very nice talk. I was wondering about, there are all these canonical sort of corner cases in hybrid systems, and one of them is this notion of chattering behavior, which is often state-induced. And so I wondered whether setting bounds on the happenings of these event changes would limit your ability to sort of capture behavior where you're chattering back and forth, or where there's some cyclicity, and whether perhaps what you have done is restricted to some sort of acyclic causal chains. And if that doesn't make sense, I can ask you offline afterwards.
So we have some ideas to take care of cyclic change. One is Lipschitz continuity, or determining if the function is monotonic, or a Taylor series expansion. But we can talk about that more afterwards if you like.
Okay, sure.
Last questions? So just quickly, you said that if the derivative was not linear, you couldn't check it for zero crossing.
So if
you said you're restricted to having a derivative that was linear, right, for one of the checks.
Yeah.
But if you have an SMT solver, right, presumably it can handle polynomials, and you could call it for those checks.
So we're only describing the variables at the happenings, so those are the only ones about which we can describe constraints. If we wanted to ensure that over the whole interval that it was valid, we would then have to discretize and check interpolating along. But we don't perform any discretization.
Okay. Okay, let's thank our speaker.